at this extension 2 question. You can pause the video to look at the question now. Okay, so here for a certain function f of x, the graph y equals to f dash x is sketched below. So this is the function's derivative, and we know that the graph passes through 0, 0. The inverse of fx is gx. Now the first one is to sketch y equals to fx. Now we just need to integrate this function. However, if you don't know any anchor point, then it has a plus c term. However, now it passes through 0, 0, right? Then you should have one graph that's certain. Now you sketch it, because you notice how there is an asymptote in the actual derivative graph. You should draw an asymptote here in the original function. However, this is not always the case. For example, if the derivative is 1 over x, which is a hyperbola, if we integrate it, we got log x, which actually increases without a bound, and it doesn't actually have a horizontal asymptote. However, we can see that it's probably 1 over x squared or something like that, and we can safely assume that after we integrate it, it's arctan function, which is like this, and it's just a good assumption. But however, I think if you didn't draw the horizontal asymptote, as I didn't in the first time, I think you can argue for that mark. However, just for safety, I think you should draw a horizontal asymptote, because it's clear that it's not a hyperbola, it's probably a higher degree. So you should draw an asymptote, and mindful that at the origin it's 45 degrees, the tangent, because it's clear it's 1 at 0, so the gradient is 1, and so it's clear at 0. Now we are supposed to sketch the derivative of gx. So gx is the inverse of fx. So we have fx, then we should draw gx first, and then we draw the derivative graph. Now, so it's called working sketches, right? So let's draw gx first. This is fx. To draw it, we just to draw its inverse, we flip it over the y equals to x, which is this point. We change it here. This point we change it to here, and then we can basically just connect it with the right shape. Now we reach it here. Now note that it's still 45 degrees, because if you flip 45 degrees, it's still 45 degrees, which is why this is special. Now we find the derivative graph of g of x, which will lead us to something like this. Notice how I used horizontal asymptote here. It's very important, because we notice here that the original function has a vertical asymptote. It absolutely will have infinite gradients, so you should have a horizontal asymptote here. Now, the sample answer is trying to show that you can simply draw the graph of this one by saying that it's the reciprocal of this one. This is completely wrong, and I think those who wrote the sample answer was unaware of this. Now, let's look at this closely. If gx is the inverse of fx, is the derivative of gx simply 1 over the derivative of fx is not true. Look at this counter example. Fx equals to sine tangent theta, gx equals to inverse tangent theta. If we actually find the derivative of these, it's like this. So are they inverse? So clearly not. I use GeoGebra to graph this. It's not. And why I use this example? Because I assumed g-x is the one in the graph, because it looks like it very much, it looks like it a lot, and then we can see that there is an asymptote for sec x, right? If you graph it correctly, it should have a asymptote here. Now we basically finish it, and it's proved by counterexample, so it's not very intuitive. Let's look at an intuitive proof of why it's wrong. This one is everyone should know, but let me just teach you how I memorize it. So we are supposed to find the derivative of an inverse function. Now I just draw two functions. This is the inverse function, it's ln x. This is the original function e to the power of x. I would like to find the derivative of the inverse function. So if I actually have a tangent here, its gradient multiplied by the gradient here, which is the point flipped through the y equals to x. These two gradients, if you multiply them, they will be 1. You can prove it using vectors, but I won't here, because if you flip them through the y equals to x axis, and if they are actually like two gradients, they will equals to 1. So now here at this point, I call it x f inverse of x. After I flip it, it will be f inverse of x, x. Now if I want to find the derivative of the inverse function, so I know that these 2 points, their gradient, if multiplied, will be 1, so I can simply find the gradient here. If I want to find the gradient here, I just chuck this value into the derivative of fx. So it's like this. Then I get this result, which after you visualize, like what I did, should be intuitive and should be memorizable. And just by observing, if it's like this, which those who write the sample answer thought so, then it's only true when x equals to f inverse of x, which is y equals to x. So this is a very, very wrong conclusion. This is a wrong conclusion, and if you're asked to prove it wrong, use counterexample, or you can use this. However, if it's a multiple choice, it says, is it correct? It's correct for some functions, which is y equals to x, then it's correct because the function is equal to the inverse function. Now let's look at this. I think you can pause the video to see, and you can see that it's from ChatGPT, but it doesn't diminish its validity. Basically, if fx has a horizontal asymptote, then its derivative has a horizontal asymptote. This is correct because if you think about it, it has a horizontal asymptote, then its gradient is approaching 0 there, then the gradient will approach 0, so the derivative will approach 0. Now this one, f dash x has a horizontal asymptote. This does not mean fx has one. It's tricky, and you can prove by counterexample as what I've just said, and I think you should pause and read it. So the vertical one is 2 of them are true except for some special conditions, so I won't actually go through it. You can think about it yourself. If fx has a vertical asymptote, then if you draw the gradient, it will approach infinity, so f dash x must have a vertical asymptote as well. So the converse one, if let's assume it's continuous and differentiable throughout the domain, then if f dash x it actually has a vertical asymptote, then that means that it will approach infinity as well. So if it approaches infinity, then the original function will approach infinity because it's increasing without bound. So lastly, I think it's, why do you think they made that question? Because it's in the 2019 HSE multiple choice 4U paper. They had a very similar question, which I would make another video on. See, it's 2020, so they've learned from last year's HSE. So that's why I think, although people always say HSE is easy, it's not easy at all, because the questions are new. You haven't seen these type of questions. Trials, although you think it's hard, they have all these new type of questions, but they actually learn from the HSE. The HSE have these new and weird questions, but the trials does not. So that's why I think HSE is always hard. It's not easy. Don't say that if you do well in trials, you'll do well in HSC. It's not how it works. So this is absolutely a great question that you can think about, and it also underlines how trials can learn from the HSC. Also that actually the teacher who wrote the sample answer they did it in the wrong way. Let me show you how they wrote it. So they said it's too confusing using algebraic proof unless use dummy variables, but you can't prove something that's wrong, isn't it? So that teacher needs to actually learn how to make simple answers and actually learn to learn these questions from the HSC, know how it works before putting it into their own trials. So see, they didn't draw the asymptote, which shows that they didn't think about it. And however, you should know about it because you've seen this video. Now, that's all, and thanks for watching.